read this?
In general, are the minimum power requirement of the elevator car ascending at a constant velocity greater than, less than, or equal to the minimum power requirement of an elevator car descending at constant velocity?
Okay. Uh, in general, the minimum power requirement of an elevator car ascending at a constant velocity, is it the same or is it different from the minimum power when it is descending, when it's going down? I mean, logically, you don't look at the calculation. This force equals the power equals the force multiplied by velocity. You don't look at this one, but we try to think logically. Now, if you are going up, you are actually pulling the full weight, right? The cable is actually pulling the full weight. So you're exerting a very big force. So you need a bigger power. Now, when you are moving downwards, the cable is not exerting a big force because it is being held by the weight of the elevator and the passenger. Okay, the passenger and the elevator is also moving down, so you need less power, right? Going up, you need more power. Going down, the the motor is held by the weight of the passenger and the elevator, so you need less power, right? So the answer is going up requires greater power than required for descending. So moving up is greater than descending, right? Moving up is greater. The question here is moving up, the question here. As elevator car ascending means moving up. So moving up, man, it has to be greater than the descending one, right? If you try to explain it, okay, so we look at the explanation here. The descending journey is assisted by the gravitational potential energy. The power is used to hold back the free fall, the difference between the weight of the object and the frictional force, right? So it means that when the elevator is going down, it is not free fall. The elevator is moving down at maybe acceleration or constant velocity. Let's say acceleration. Okay, it's accelerating downward, but it's less than 9.8 meter per second. It means that the cable has to pull back the load to prevent it from falling down freely. So you have to hold back the load. Not only the power is used to hold back the load, it is also used to overcome the friction, right? The friction of the cable. So the power of the motor is used to hold back the weight and also the friction, right? What? How about you hold back the weight, then you don't need the full power, right? Part of it don't need. Part of the mg, right? You don't need the full mg to make it accelerate downward. In order to understand what I'm talking about here, then you look at this diagram, the diagram over here. Okay, right. So in the diagram here, the cable is pulling the thing upward, holding it back, preventing it from falling freely. Then the weight of the object is asking it to move down. The tension is holding it back, don't want to let it fall freely. Okay. Then the next one is the frictional force, this one. So the one at the side. This frictional force, whichever the direction also there will be frictional force opposing the motion. Since you are moving down, so the frictional force is opposing, is moving up, right? It's moving up. So these two forces, they are balanced by the weight, or rather these two balance the weight. These two forces balance the weight. So we can have something like this, right? So we say that this mg equals to, hey, why you got the, okay, we say this weight here is balanced by the tension in the cable and also the frictional force. So if you want to calculate the tension in the cable, so the tension in the cable is actually, you move the F over to the other side. So it's mg minus F. So if you look at this equation here, mg minus F, mg minus F, and I put it over on this side, mg minus F. So this is actually the tension in the cable, and this tension in the cable is provided by the motor, right? This tension is, now if you compare it with the earlier case, the tension in the cable is mg plus F, but when it's going down, it's mg minus F. So the force used is less. The force used when it is moving upward is more. The force used when it is moving downward is less, right? So that's why the power is less when it is moving down, because the cable, the motor is actually exerting a smaller force. This one, the motor has to exert a bigger force. Okay, so this settle the problem here, whether it is greater or less. Moving up is greater than descending. Ascending is greater than descending. Right? Answer is A. Let me include one. Answer is A, right? Answer is A, greater. What is greater? Ascending. Ascending. Yes, okay, ascending. Ascending power greater than the power required for descending. The reason is because it has a bigger force. Descending, less force. Okay. Now we do the actual calculation. We do actual calculation. You read this exercise 5.12.
Suppose the same elevator car with the same load descends at 3 meters per second. What minimum power is required here? The motor removes energy from the elevator car by not allowing it to fall freely.
Okay, right. So the question is, I want to highlight a few points here. First one is the same elevator is used. Same elevator used, that means the mass is the same. Mass of the passenger and the mass of the elevator is the same. The second thing I want to highlight here is the 3 meter per second. It means that the the whole system is moving at a constant velocity. So there is no net force. The forces, they balance one another. So what is the minimum power required? Here the motor removes energy from the elevator by not allowing it to fall freely. What does this mean? Not allowing it to fall freely? It means that, oh, why should I need power to move the thing down? Right? Now you may, in the first case, just let it fall down lah. The motor doesn't need to do any work, and you don't need to turn on the motor at all. You can just switch off the motor. Why so stupid want to use power to move it down? Okay, Now the reason is if you you switch off the power, you allow the elevator to go down, you will fall freely and you will achieve a very high speed. And by the time it reaches the ground, you cannot control it. You cannot slow it down. So it will crash and everything shatter into pieces. So that's why the cable is needed. The cable is needed to hold back the elevator, don't to prevent it from falling down freely. So the power is actually used to pull back. It's not used to assist the fall. It is actually used to hold back the free fall, right? Oppose the free fall. Okay, so this is what they're talking about, right? Moto remove the energy from the elevator by not allowing it to fall freely, right? That's what they're talking about. So this is the explanation, but the 2 points that I want to highlight here is the weight remains the same and it is moving down with a constant velocity. That means there's no net force. So we're going to calculate what is the force used to hold back the elevator. So the force used to hold back the elevator is the tension in the cable. This tension in the cable is the weight minus the frictional force. The weight minus the frictional force. Okay. So what is the weight? 1,800 multiplied with 9.8. 1,800, the mass multiplied with the acceleration due to gravity. So this is the weight. What is the frictional force? 4,000 newtons. 4,000 newtons. So you use the weight minus the frictional force. It is 13,640 newtons. But the book, they round off to 13,600 newtons only. Actually, there's a 40 there, but the book round off to 600. Okay, so this is the force exerted by the motor to hold back the free fall. Okay, then what is the power? Power is the force multiplied with the velocity. Now the force is this one, 13640. Velocity, 3 meter per second. 3 meter per second. So multiply this together. Answer is 40.9 kilowatt. If you want to convert to horsepower, then you use 4.9 kilowatt divided by 746. So answer is 54.8 horsepower. Any question